video, what we're going to talk about is random variables and how to create random variables in R. And so basically, the first thing that we will talk about is random variables. So a random variable is a rule that assigns a number to the outcome of a random process. That's what a random variable is. And so what we're going to do is we're going to go through how to create a random variable with the different distributions in R that you can create with R. So we're going to create a random variable using the Bernoulli distribution. So X becomes R binom. So R is for random variable. In binom is for binomial distribution, brackets 1000, comma, size equals 1, comma, prob, that's your probability, equals 0.3. So we're going to create a histogram of this random variable X, and the color is going to be blue. So here is our histogram that we have created. So if the probability is 0.3, you can see that 0 is going to be 0.7, and 1 is going to be 0.3 because you've got a probability of 0.3. So the next thing we're going to do is we're going to create a random variable with a binomial distribution. So the binomial distribution is the number of successes in independent binomial trials. But hold on one second. Let's just check something. So we were talking about the Bernoulli distribution, and the Bernoulli distribution models a single trial with two outcomes being success or failure. So the binomial distribution and the Bernoulli distribution are related, because you can see with the Bernoulli distribution, you have R binom brackets 1000, comma, size equals 1, comma, probability equals 0.3. So we're going to go to the binomial distribution, which is a number of successes in independent Bernoulli trials. So the binomial distribution and the Bernoulli distribution are related. So X becomes R binom brackets 1000, comma, size equals 10, comma, probability equals 0.5. So in the Bernoulli distribution, you had a size of 1, and the binomial distribution, you have a size of 10. So that is the major difference between the Bernoulli distribution and the binomial distribution. And then when you have a probability of 0.5, then that's going to be close to a normal distribution. But what we can come over here, what we'll go over here, back over here to the Bernoulli distribution, and we're going to make the Bernoulli distribution as a probability of 0.5, and we're going to run it. And so we're just running it. So you can see that with the Bernoulli distribution with a probability of 0.5, you have one column of data, or one bar is 0.5 and the other bar is 0.5, whereas the previous distribution that we made, it was 30% probability, so you had the 0 bar being 0.7 and the 1 bar being 0.3. But with a probability of 50%, the 0 bar and the 1 bar are the same. So I thought it would be good to give you a 50% probability so you can look at the Bernoulli distribution, and you can see that the distribution that is created with a size of 10, and a probability of 0.5 and the number of samples is 1,000, you can see it looks like a close to a normal distribution. So that's how you can see that the Bernoulli distribution and the binomial distribution are related to each other. So now we're going to check the Poisson distribution. So a Poisson distribution counts how many events occur in a fixed interval when events happen at a constant average rate. So we're going to run that in R, being X becomes R Poisson brackets 1,000, comma, lambda equals 4. And then you're going to make a histogram of that. So X, hist brackets X, comma, color equals green. So lambda equals 4. So you can see that when your lambda equals 4, you can see that the distribution made is right skewed. But let's change our lambda over to 2 because your lambda is what changes the shape of the distribution. So let's make a lambda equals 2. So you can see with a lambda equals 2, you can see that the Poisson distribution is still skewed to the right. But let's make a lambda equals 5. Okay, so it's skewed to the right. It's still skewed to the right. Let's try one more thing. Let's make a lambda equals 10. So when you have a lambda equals 10, the Poisson distribution resembles a normal distribution. So let's go back to lambda equals 5. Okay, and so when the lambda equals 5, it's skewed to the right. So that just gives you an idea that when you change the lambda, it's going to change the shape of the distribution. So now we're going to create a random variable from the geometric distribution, which is the number of trials needed to get the first success. So we're going to create that in R. X becomes R geom, and R is for your random variable, and geom is for geometric, brackets 100, comma, probability equals 0.2. And we're going to create a histogram of the distribution that is made. So hist brackets X, column color equals light green. So with a probability of 0.2, you still have a right skewed distribution. So let's just say a probability of 0.5 and see what comes up. It's still right skewed. Let's try a probability of 0.7. Still right skewed. So let's go back to 0.2. Okay, so it's still a right skewed distribution. So now we're going to create a random variable with a negative binomial distribution. So previously we had created a random variable with a binomial distribution, and now we're going to create a random variable with a negative binomial distribution. Negative binomial distribution is the number of trials needed to achieve K success. So R becomes R in binom. R is your random variable, in binom is negative binomial, brackets 1,000, that's 1,000 samples, comma, size equals 5, probability equals 0.4. And so we're going to run it and make a histogram. And so you can see that it is right skewed. So let's say a probability of 0.2. Let's see what happens when we have a probability of 0.2. It's still right skewed, but let's go over here let's go back to the first binomial distribution. So let's make it a size of 10 and probability of 0.5 and see what we come up with. So we're going to make it a size of 10 and probability of 0.5. So it's still skewed to the right. It's still skewed to the right when you have a size of 10 and a probability of 0.5. So let's make it 0.2 and see what happens. Okay. Okay, so it's still right skewed. So that's your negative binomial distribution. So now we're going to create a random variable on the hypergeometric distribution. Hypergeometric distribution is the number of successes and draws without replacement. So basically what happens is, which we've discussed in previous videos, when you are sampling an item, you can have sampling with replacement and sampling without replacement. So sampling with replacement means that when you take a sample, you replace that number that you just sampled. A sample without replacement is you take the sample and you don't replace it. So we're going to use R to create this random variable. The X becomes R hyper, brackets 1000, comma M equals 20, comma N equals 30, comma K equals 10. And we're going to make a histogram of that being light yellow. Doesn't look like light yellow to me, but it is. And so this is the histogram that is created from that. And so you can experiment with the M, N, and K, and that will give you different distributions. And so we're going to create a random variable with a discrete uniform distribution. So our uniform distribution is all of the equal length have equal probability. So you create this random variable with X becomes sample brackets 1 to 6, comma 1000, replace equals true. So you're sampling with replacement. And we're going to create a histogram of that. So brackets X, comma, color equals pink. And so you can see that the vertical bars created are very similar in length. So now we're going to create a random variable with uniform distribution. So this one that we're creating here is also a uniform distribution, but you're using the sample command, the sample function. But we're creating another uniform distribution and using the unif function. So X becomes R unif. So that's a random variable, uniform, brackets 1000, comma, min equals 0, comma, max equals 1. So you're going to have 1000 samples of any value between 0 and 1. And we're going to create a histogram of that. So hist brackets X, comma, color equals light pink. And so you can see that the vertical bars created are very similar in length. And that's what the uniform distribution is all about. So now we're going to create a random variable normal. So we're going to use the normal distribution. A normal or a Gaussian distribution is the famous bell curve and models many natural phenomena. So X becomes our norm. So that's random variable of a normal distribution. Brackets 1000, that's 1000 samples, comma, mean equals 0, that should mean, comma, ST, that's your standard deviation, equals 1, and we're going to create a histogram of that. And so hist brackets X, comma, color equals red. So you can see this is our bell curve. But let's make the mean of 5 and the standard deviation of 10. And let's see how that changes your bell curve. So it looks like you get a little bit of a different bell curve. So let's try a mean of 5 and a standard deviation of 5 and see what we come up with. So again, you can see that the bell curve is a little bit different. So you can experiment with that. So we can say, go back to mean of 0, standard deviation of 1, and that's generally your standard bell curve. But you can experiment with the different means and standard deviations to give you any bell curve that you like. So now we're going to create a random variable with the exponential distribution. So the exponential distribution models waiting times between many independent events. So X becomes R EXP brackets 1000 comma rate equals 2, and we're going to run that, create a histogram of that. So hist brackets X comma color equals orange. And so this is your exponential distribution, but we can change that around a little bit. Let's make the rate of 5 and see what happens when we make the rate of 5. So you can see the exponential distribution is a little bit different when we change the rate. And let's make the rate 1. Okay, so when the rate equals 1, you can see that the exponential distribution is also different. So you can experiment with the rate to get different random variables. Now we're going to create a random variable using the gamma distribution. So the gamma distribution is a generalization of the exponential distribution and is used for waiting times of multiple events. So X becomes R gamma, so that's a random sample of the gamma distribution, brackets 1000, that's your samples, comma, shape equals 3, comma, rate equals 1, and you're going to create a histogram of that. So hist brackets X, comma, color equals purple, and so you can see you've got a distribution that is skewed to the right, and so you can change the shape and the rate to get a different type of distribution. And now we're going to create a random variable with a chi-square distribution. Chi-square distribution is a sum of square normal variables and is used in hypothesis testing. So X becomes R chi-square brackets 100, comma, DF, that's your degree of freedom, equals 4. So hist, we're going to create a histogram of that. So hist brackets X, comma, color equals cyan. So you've got 4 degrees of freedoms, and again, you've got that skewed to the right. So let's make a 2 degree of freedom and see what happens. So when you've got 2 degrees of freedoms, you can see that it creates a different type of distribution. So now we're going to create a random variable with the t-distribution. So your student's t-distribution is used for estimating means with small samples. So X becomes RT, so that's a randomly sampled t-distribution, brackets 1000, comma, DF equals 10, and the color is going to be maroon. We're going to create a histogram of that. So hist brackets X, comma, color equals maroon. And so you can see that this is your student's t-distribution. So let's try a degree of freedom of 5 and see what we get. So when you have a degree of freedom of 5, the distribution created is similar to a normal distribution. And that's the difference between a normal distribution and a t-distribution. A t-distribution is similar to a normal distribution except for the fact that it has fat tails. So now we're going to create a random variable with the f distribution. So the f distribution is a ratio of two squared chi-squared variables using the ANOVA. ANOVA is analysis of variance. So x becomes RF, that's a randomly selected f distribution, brackets 100, 1000, that's your samples, comma, df1 equals 5, and df2 equals 10. So df1, I believe, is your numerator, and df2 is your denominator. And we're going to put that into a histogram. So hist brackets x comma color equals sky blue. And so you can see this is the distribution that is made from a f distribution. And you can change the f distribution by changing df1 and df2. So we're going to change df2 to 5 here. And you can see that the distribution has changed. So let's make this df2 as 20. So you can see that this is the denominator of 20. So you can experiment with the different df1s and df2s to get you different distributions. And now we're going to create a random variable with the beta distribution. So the beta distribution models probabilities and proportions with values between 0 and 1. So we're going to create a variable, random variable. So x becomes r beta, that's randomly select sampled beta distribution, brackets 1000, comma, shape 1 equals 2, comma, shape 2 equals 5. We're going to create a histogram of that. So hist brackets x equals color equals green. So this is the histogram that has been created, and you can see it is skewed to the right. So we'll make shape 2 as 2 and see what we come up with. So this is 2. So that's a little bit different than the first one that we did. So let's say shape 2 is 4. So you can see that that's right skewed. So we'll go back to shape 2, shape 1 being 2, shape 2 being 2. And you can see that that's a different type of shape as well. So you can experiment with shape 1 and shape 2 to give you different types of distributions. So now we're going to create a random variable with a log normal. Log normal distribution is a variable whose logarithm is normal. So x becomes RL norm. So that's a randomly selected log normal distribution, brackets 1000 equals 1000 samples, comma, mean log equals 0, comma, st log equals 1. So that means 0, mean is 0, and standard deviation is 1, which is different from your normal distribution. And we're going to create a histogram of that. So hist brackets x, comma, color equals goldenrod. So this is your log mean, your log, a log normal. So you can see that that's what it looks like with a log normal. And you can experiment with your mean and your standard deviation to change the shape of the distribution. So that is it for creating variables, random variables in R. I've used all the distributions that I could think of. And there may be some more distributions in R, but I'm not aware of it. But what I would suggest you do is you experiment with these different types of distributions and the different hyperparameters to change the distributions to what you would like. So that concludes this video. The next video is going to be on another statistical topic, and I hope you decide to watch it.